Okay, this is the second part of my talk. We're going to be discussing the proof of this theorem. There are three main parts to it. First, we need to show that C dagger is hyperbolic. Then we need to provide lots of loxodromic elements of diff naught of S on C dagger. And then we need to make sure that there are two independent loxodromics in order to satisfy the condition of Besselian and Fujiwara. Let's start with the hyperbolicity of C dagger. So what we're going to do is we're going to approximate the distances between four vertices in C dagger using the distances in certain graphs which happen to be hyperbolic with an absolute constant delta. And then by something called the 4-point condition, we can then deduce that C dagger is hyperbolic. So what are these graphs that we're going to use? These are called the surviving curve graphs. So I'm going to define this when the genus is at least 2 for simplicity. It can also be defined for genus 1. So let S be a closed surface, genus at least 2, and let P be a finite set of points. Then we're going to consider the surface S minus P, which is a punctured surface. It's also a finite type. And we're going to consider the subgraph of the curve graph, the ordinary curve graph. So this has vertices, which have isotopic classes of simple closed curves in S minus P that are not null homotopic in S. So it's almost the same definition as the ordinary curve graph, but you're only focusing on a subset of the vertices. And you have edges when two vertices admit disjoint representatives. So in other words, the underlying curves can be isotoped on S minus P to be disjoint. Now the ordinary curve graph, which is just denoted by C, was proved to be hyperbolic by Mazur and Minsky. This is a very important theorem. But today we will need that the hyperbolicity constant doesn't depend on the surface. And the first such result in this direction was that curve graphs were proved to be hyperbolic with an absolute constant delta. This was shown by various people independently and around the same time: Tarek Al-Gab, Bowden, Clay, Raffi, and Schleimer, Hensel, Shatitsky, and myself. Later on, Shatitsky and Sisto gave a purely curve surgery theoretic proof based on the ideas of Hensel, Shatitsky, and myself earlier. Alexander Rasmussen used these curve surgeries to show, with a harder argument, it turns out, because these graphs are harder to understand, that there is this absolute constant delta such that the surviving curve graphs are delta hyperbolic whenever S is some closed surface of genus at least 1 and P is a finite subset. So this is important for us today. And so let me just remind ourselves what we're going to do. We're going to pick any 4 vertices in C dagger, and then we're going to show that these distances between the alpha I in C dagger is uniformly approximated by some distances dvi vj in some delta hyperbolic space. It turns out to be some surviving curve graph of S minus P. And that allows us to deduce that C dagger is hyperbolic by the 4-point condition. So how do we do this? First of all, we want to make sure that our curves alpha I and alpha j are pairwise transverse. So to do that, we just take an alpha I, we take a curve alpha I, and we move it off itself, and then we can just perturb it to ensure it's transverse with the other curves. So in the graph, we're taking a vertex and we're taking a neighbor of it in order to ensure that these curves are transverse. And when you do that, the distances in C dagger could change. So you get errors creeping in of plus or minus 2, but that's fine because that's uniform. So after we do that, we can assume the alpha-I are transverse. And therefore, there are only finitely many complementary regions to the union of these four curves. And then we puncture each component in the complement of the curves. There are only finitely many complements, so there'll be finitely many punches. Here's an example. Got some curves on the surface. They might intersect really badly and far from minimally in their isotopy classes. In other words, there are bigons on the surface, but we just put a puncture in each complementary region. Now the next step is to consider these curves as isotopy classes on the punctured surface. This gives us vertices in the surviving curve graph of S minus P. And it turns out that the distances between the alpha I and alpha J are now precisely the distances in C dagger. And that's great. And now if we just assume that for a moment, then we're done by Alexander Rasmussen's theorem and the 4-point condition. Because the distances in CSS minus P, because it's hyperbolic, behaves like the distances in a tree up to some uniformly bounded error, and so the distances here also behave like distances in a tree up to uniformly bounded error, so C dagger's hyperbolic. So now we're done, provided we prove step 3. So let's see why step 3 is true. Well, there are two inequalities we need to show. This one turns out to be much easier and is more or less always true for any choice of P. So the observation to make is that any path in C dagger gives you a path between these endpoints in the surviving curve graph. That's because we can project alpha I and any vertex, as long as it's disjoint from P, to its isotopy class in S minus P. And notice that adjacent vertices will get mapped to adjacent vertices in the surviving curve graph. So that side of the equation is straightforward. Less straightforward is the other inequality. This one, you need the puncture set P to be large enough in a certain sense. You need to choose your puncture set to be big enough so that alpha I and alpha J are in minimal position on the surface minus P. Minimal position means that the curves intersect minimally in the isotopy classes on S minus P. There's this lemma called the bigon criterion, which states that two curves are in minimal position if and only if they share no bigons between them. So here's a bigon, for example, between these two curves. But if you puncture the bigon, then that doesn't count as a bigon anymore. So all of these curves here turn out to be in minimal position. So just by putting in enough punctures, you can ensure that curves are pairwise in minimal position in S minus P. That's all well and good, but now we need to ensure that paths in the surviving curve graph can be lifted to paths in C dagger. And that turns out to be true. So given any path, or geodesic, the vertices between alpha I and alpha J, their isotopy classes in S minus P, as long as these are surviving curve graph vertices, then what we can do is we can find, by induction, representatives of these curves on the surface S, such that any two consecutive curves are in fact disjoint on S. And that is precisely what we need to lift any path here to a path in C dagger. And so we get the opposite inequality. How does this proof work? Well, you just start with the collection of curves. And if they're not in middle position, then you find a bigone, you choose an innermost bigone. The bigone can't be between the endpoint vertices. It must be between some vi and some other vertex. And then you just try to remove the bigone while keeping everything else fixed and make sure that the number of intersections goes down. And just repeat that argument. And eventually you must end up with these curves pairwise in middle position. So that's the proof of hyperbolicity done. Where do our loxodromics on C dagger come from? They come from mapping class groups. So Thurston introduced this notion of pseudo-Anosov mapping class in the late 70s. It's a mapping class that has a representative homeomorphism that is Anosov outside finitely many points. So Anosov means that there's this fixed constant lambda called the stretch factor, such that the map stretches one direction by lambda and contracts it by lambda, or stretches it by 1 over lambda. Lambda is strictly greater than 1. What about some pictures of pseudo-Anosovs? Well, they're actually quite a natural thing that appear in many different situations. So I've stolen this picture from Jean-Luc Tiffo's Twitter. This picture comes from a 1905 patent for a taffy pulling machine. Now you can see that there are some singularities where the map isn't pseudo-Anosov, but most other points the map is pseudo-Anosov because the taffy is being stretched this way and contract the other. Now we need our maps to be in diff naught of S, so we need them to be isotopic to the identity on the surface. So in other words, we need these mapping classes to be in the kernel of the natural map of the mapping class group of S minus P to the mapping class group of S, or the forgetful map, or the Bernemann kernel. The fact that these pseudo-Anosov maps do exist is essentially due to Kra, but there's also another way of proving it using work of Yeber Mackay. And so the idea now for us will be to pick any representative of such a pseudo-Anosov mapping class on S minus P. Any such representative, as long as it preserves the fixed points of P, and show that that map will be loxodromic on C dagger. Why should that be true? Well, first of all, F being pseudo-Anosov in the mapping class of S minus P implies that it's loxodromic on the curve graph of S minus P. This is a theorem of Mazur and Minsky, and indeed, saying that this is loxodromic on the curve graph makes sense because Mazur and Minsky proved it's hyperbolic. But observe that the surviving curve graph is a subgraph of the curve graph, and so we automatically get F loxodromic on the surviving curve graph too. It's great. But we saw this Lipschitz projection earlier of C dagger onto the surviving curve graph. And so using that, we can deduce that F is loxodromic on C dagger too. In fact, the asymptotic translation length on F on the curve graph gives us a lower bound for the asymptotic translation length on C dagger. If you pick your representative diffeomorphism of the pseudo-Anosov really badly, then the asymptotic translation length on C dagger can in fact be way bigger than the asymptotic translation length of the isotopy class on the curve graph of S minus P. So this inequality is by no means sharp. So that's where our loxodromics will come from. How do we get independent loxodromics? Well, let's just make some observations for a start. So there is a one Lipschitz map from C dagger to C, which is equivariant with respect to the group action by the diffeomorphisms. So diffeomorphisms of S acts on C dagger, it also acts on the curve graph. And pi respects this action. Then you notice that diff naught of S, by definition, does absolutely nothing to the curve graph. In other words, f of the alpha isotopic class of alpha is just the isotopic class of alpha. So now just suppose that we have two dependent loxodromic elements of diff naught. Well, then we can always find an H diff naught such that HAF fellow travels AG for a very long time, for some arbitrary distance. Let's draw a picture. Suppose AF and AG are dependent loxodromics. Then I can make HAF fellow travel AG arbitrarily much. But then notice, since these are loxodromics in diff naught, when you have your axis HF and you project downstairs, this line will project to a loop because diff naught does nothing on the curve graph, but it does something to C dagger upstairs. The same is true for AG. And so if you make them fellow travel for long enough, then in fact what that does, what you see when you map the two axes by this Lipschitz projection pi, you'll get two bounded loops, which are bounded distance from each other in the ordinary curve graph. And that's what this lemma is stating. So if you see HAF fellow traveling AG for a long time, sufficiently long, then notice that pi AF and pi AG are uniformly bounded from each other in the ordinary curve graph of S, but the constants depend only on the hyperbolicity constant and the quality of the axes AF and AG, because they're quasi-axes, they're quasi-geodesics. So the constants depend on the quality of these quasi-geodesics. Observe also, since H is in diff naught, pi of HAF is the same as pi AF. So what we need now to find independent loxodromic elements in diff naught, we just need to make sure that the conclusion of this lemma fails. So this is what we're going to do. We're going to take any loxodromic F in diff naught, and then conjugate F by some pseudo-Anosov on the whole surface, B, and then raise it to some large power e to the n. So we're going to consider this conjugate. It lies in diff naught still, because diff naught is normal. B is in diff, it's outside diff naught. We want this to be a representative of some pseudo-Anosov mapping class of the mapping class group of S. We choose the axis of this loxodromic to be the left translate of the axis of F. That's just property that you can do using tricks with conjugation. And then this axis will have the same quality as AF. So that's just fixed. The qualities of these axes are fixed. But by taking powers of B, we can ensure that this is arbitrarily far from pi AF, using the fact that the action of a pseudo-Anosov mapping class on the ordinary curve graph is loxodromic. So these are now arbitrarily far away, And so the conclusion of the lemma fails, and so the hypothesis of the lemma must fail. Namely, we must have f and this large conjugate of f independent in diff naught. In fact, it's far from being dependent because we can't even get HAF, where H is in diff naught, anywhere close to b to the n of AF. Because indeed these are far away in the ordinary curve there. Okay, so that's how we prove that certain loxodromics are independent. In our first version of our paper on arXiv, we found and constructed independent loxodromics that were independent in diff. That was much harder, but it can be done. But today we just went for this neat proof for diff naught. Okay, that's all I have to say. Thank you very much for listening.